Welcome to Dose of Data. I'm your host, and today we're diving deep into entity resolution on real, messy data.
Happy to be here. We'll talk about what it actually takes to dedupe millions of records, where the open source tools break, and what the numbers really look like when you stop using toy dataset.
34 seconds. That's how long it took to run a full data quality pipeline on 208,000 real voter registration records. Not 200 rows of fake data, not a toy demo. Wake County, North Carolina, Raleigh, and the surrounding area. And the system found 10,718 duplicate clusters, cleaned 197,000 addresses, and flagged 61 quality problems. 34 seconds. I'm your host, and today I'm talking to the person who built and ran all of this. Welcome.
Thanks for having me. And I want to be honest up front, 34 seconds sounds like marketing copy, but it's a real number on a real machine with real public data. Anyone can download that Wake County voter file from the NC State Board of Elections and run it themselves.
Let's start with the obvious question. Why does any of this matter? Entity resolution, data quality pipelines, these sound like enterprise IT problems. Who actually gets hurt when this stuff breaks?
The clearest example I know is healthcare. I spent time with the NPPES dataset, that's the National Plan and Provider Enumeration System, the U.S. registry of every licensed healthcare provider, 6 million records, updated monthly, and names are spelled 4 different ways across quarterly updates. You've got enough Smiths and Garcias to break any blocking algorithm. When a health system tries to match that to their internal records and gets it wrong, a patient's provider history gets fragmented, claims get denied, referrals go to the wrong place.
And this isn't a theoretical failure mode.
No. I took 500,000 randomly sampled records from the March 2026 NPPES release and pointed 2 tools at them, dedupe, the canonical Python library, and GoldenMatch, our engine. And the first thing I learned is that before you even get to precision and recall, you have a gauntlet of configuration decisions that silently change your output.
Walk me through that. What kind of decisions?
With dedupe specifically, you have to pick which fields to match on. Pick wrong, recall tanks. You have to declare field types. String, short string, exact, price, lat long, each behaves differently. You set a sample size. You set a blocked proportion. You choose a partition threshold. 0.5, 0.3, 0.7. Dedupe will not tell you which is right for your data. And there's a bug, or I'd call it a foot gun, in dedupe 3.x where if you set index predicates equals true, you need an explicit indexing step, or it crashes mid-partition with a no-index error.
That you found the hard way.
Very much the hard way. Halfway through a 500K record run. And the frustrating thing is none of these questions have definitively wrong answers. They just silently shape the output. If your labeler is inconsistent, or if you're writing a deterministic labeling rule as a proxy for interactive labeling, that propagates all the way through the model.
Okay, so let's rewind and talk about the actual tooling landscape before we get deep into your work. There are 4 serious Python libraries for entity resolution. Can you give me the 30-second version of each?
Sure. Splink is the most statistically rigorous. It's built on the Febrl probabilistic model, uses DuckDB or Spark or Athena as a SQL backend, estimates match weights via expectation maximization, and gives you calibrated probabilities. If you need to defend your matching decisions to a regulator, Splink is where you go.
And dedupe?
Dedupe is the oldest. Active learning, you label pairs interactively, it trains a classifier, then partitions your data. Genuinely clever approach. The issue is that interactive labeling is hard to automate, and when you can't automate it, you're bottlenecked by whoever is doing the labeling.
RecordLinkage?
Clean scikit-learn style API. Indexer, comparator, classifier. Well documented, but it hasn't been updated since July 2023. That's not necessarily fatal, but it means no one is fixing edge cases.
And GoldenMatch is yours, so you're biased. But tell me anyway.
Configuration-driven weighted scoring. You write a config with blocking rules and match keys. It handles scoring, clustering, optional LLM calibration. No training data required. The trade-off is you still have to write the config. We tried zero config on all 3 benchmark datasets, and it failed on all 3. So I'm not going to tell you it's magic. What it does well is give you explicit levers, and it runs in-memory plus ANN blocking for scale.
You benchmarked all 4 on the same 3 datasets. What were the datasets?
Febrl 5000 synthetic personal records with controlled noise. DBLP-ACM, 4,910 bibliographic records, paper titles, authors, venues, and a 10,000 record sample of the NC voter file, which has no ground truth, so that one is a robustness test more than an accuracy test. Febrl is the warm-up. DBLP-ACM is harder because paper titles require something closer to semantic understanding. The voter data is the real-world stress test.
Before we get into where GoldenMatch sits on those benchmarks, I want to understand what the suite actually does end-to-end. You ran the Wake County voter file through it. Walk me through what happens.
3 stages. GoldenCheck first, that's the profiler. It scans every column and reports quality issues without touching the data. On 208,505 rows with 11 columns, it finished in 1.1 seconds and found 61 findings.
What kind of findings?
Date format inconsistencies, 208,497 dates in MMD DDV OI format, and 4 in YDOMAL-ish MADD. GoldenCheck flags the minority pattern as a consistency issue. Numeric columns that should be strings, zip codes, and phone numbers stored as integers, which means a Connecticut zip code starting with 0 would lose the leading 0 silently. Encoding issues, 18 street addresses with non-ASCII characters. And this interesting one, data drift.
Data drift from a voter file?
The file is sorted alphabetically by last name. So GoldenCheck's drift detector sees 7,067 first names appearing only in the second half of the data, because names starting with M through Z have different distributions than A through L. It's an artifact of the sort, not a real quality problem, but GoldenCheck correctly flags it for review. That's the right behavior. It surfaces the anomaly and lets you decide.
Then stage 2 is GoldenFlow.
GoldenFlow reads the GoldenCheck findings and decides what to fix. It ran 41 transforms on that dataset, but only 5 actually changed data. The rest were no ops, the data was already clean for those columns.
What were the 5 that mattered?
Address white space was the big one. Nearly every address in the voter file has double spaces between the house number and street name, DR with 2 spaces instead of 1. That's a common artifact of fixed-width data exports. GoldenFlow's collapse whitespace transform fixed all 197,366 affected addresses in one pass. And date normalization, converting 208,497 dates from MMDDDIWSBEL-USH format.
And then GoldenMatch deduplicates.
Right, and that found 10,718 duplicate clusters across 208,505 records. Same person registered twice, maybe with slightly different phone format or address spelling. That's the full pipeline. Profile, clean, deduplicate. Total wall time, 34 seconds.
Let's talk about where this breaks, because you've been pretty candid about failures. The Bulldozer dataset is a good one.
Yeah, the Kaggle Bulldozer Blue Book dataset, 401,125 auction records across 53 columns. Equipment auction data is genuinely messy. The same Caterpillar D6 bulldozer sells 3 times across different states, and each auction house records the model differently. 580 Super L in one record becomes 580 SL in another. D6H LGP appears alongside D6H, same machine, different level of detail.
And the first run produced 0 matches.
0 matches. Autoconfig completely misclassified the columns. Sales ID, that's a 7-digit integer, got classified as phone because 7-digit integers look like phone numbers to a pattern profiler. Sale price 5-digit round numbers got classified as zip, and FI model desk, the single most discriminating field in the entire dataset, got dropped entirely because there's a fuzzy field limit of 5 and it appeared after 5 other columns.
So column order was the tiebreaker.
Column order was the tiebreaker, which is a terrible heuristic. We fixed that in v1.2. Please 6 fields are now ranked by cardinality times completeness times string length. FI model desk, which has high cardinality and long strings, naturally floats to the top. And we added price and cost and amount patterns to the classifier, so sale price stops getting called a zip code.
What did the result look like after you fixed the config?
27,937 duplicate clusters, 384,650 records matched. 3 blocking passes, 1 on model description soundx, 1 on base model code, 1 on year and state. Ensemble scorer taking the max of Jara-Winkler, token sort ratio, and soundx. That handles the model description variance.
You mentioned ANN hybrid blocking. What's that and why does it matter?
Standard blocking groups similar records so you only compare within groups instead of doing n-squared comparisons. But some groups get enormous. The Soundex code D000 covers every Caterpillar D-series machine in the dataset, 61,861 records. Standard blocking skips those groups because they're too big, but skipping them means missing legitimate duplicates.
So what does ANN do differently?
Approximate nearest neighbor search. Instead of processing the whole oversized block, you embed the records and find neighbors in vector space faster, and it recovers records that string blocking misses. In the Bulldozer dataset, ANN hybrid blocking recovered 949 records that string blocking missed entirely. That's the difference between finding them and not.
Let's talk about the LLM integration, because this is where things get interesting. You have LLM calibration on both the Bulldozer dataset and the UK schools dataset. What's actually happening?
Two different uses. On the UK schools dataset, that's 52,288 records from the government's Get Information About Schools register, the LLM is being used for smarter data profiling in GoldenCheck and for resolving borderline duplicate pairs in GoldenMatch. Standard GoldenCheck found 820 quality findings. LLM Boosted found 843, including 6 errors the profiler completely missed, invalid locality values with numeric characters, invalid town names. That cost 0.13 cents on the full 52K row dataset.
1 cent.
1 cent. And the LLM scorer for borderline duplicate pairs cost about 0.35 cents. So the full LLM enhancement on that dataset costs under 10 cents. That's not a marketing number, that's what we actually paid.
The Bulldozer LLM calibration is doing something different, though.
Right, that's LLM calibration for threshold learning. The matching algorithm produces a similarity score for every candidate pair, and you need a threshold. Above that score, it's a match; below, it's not. Picking that threshold is hard. Too high, you miss real duplicates. Too low, you get false positives.
How does the LLM learn it?
You show it 200 pairs, some matches, some non-matches, and it labels them. From those 200 labels, the system learns the optimal threshold for that specific dataset. On the Bulldozer data, the LLM learned the perfect threshold from 200 pairs. Total cost, 0.31 cents.
That's a remarkably cheap calibration step.
It is, and the reason it works is that you don't need 200 gold standard labels from a domain expert. You need 200 reasonably labeled pairs, and an LLM can provide those from the record content alone. The savings versus having a human label 200 Bulldozer auction records is obvious.
Let's jump to the BPID benchmark, because this is where you test it against something adversarial. Tell me what BPID is.
Amazon published BPID, Benchmark for Personal Identity Deduplication, at EMNLP 2024. It's the first open-source benchmark specifically for PII matching, 10,000 profile pairs. The whole point is that these pairs are designed to fool your matcher. Two different people named Damien Skinner and Skinner Damien sharing an email address and phone number, but with contradicting birth dates. A naive string similarity approach will confidently match them.
What does the profile look like for each record?
5 attributes. Full name, email, which is a list, phone, also a list, address, and date of birth. And the date of birth field is free text, so you get 1990, Nunhuzi 14 paired with 14 Nov 1990, same date, completely different format. About 18% of attribute values are missing. Some profiles have a single letter name and no email.
What are the published baselines?
Random forest with handcrafted features gets 0.629 F1. Ditto, that's a fine-tuned BERT model, gets 0.752. Pseudo-Wudo, which is the state-of-the-art in the paper, gets 0.788. Even Claude 3 Sonnet and GPT-4 Turbo were benchmarked. LLMs actually scored well but made systematic errors on phone number digit comparison because tokenization struggles with exact digit counts.
And GoldenMatch is not designed for pair classification. How did you adapt it?
GoldenMatch is a deduplication engine. You feed it a table and it finds clusters. So we adapted its scoring primitives for pairwise comparison. 3 configs iterating up.
Walk me through the configs.
Config 1, naive weighted scoring, using GoldenMatch's field level primitives with a list-aware scorer. That got us 0.665 F1, which is better than random forest but not great. The problem was DOB. Free text date pairs, 1990, Nunhuzi 14 versus 14 Nov 1990, were getting scored as strings, and the string similarity was low even for identical dates.
So you added date parsing.
Config 2 added explicit DOB parsing, parse both dates to a canonical format, then compare. That lifted the score meaningfully, because DOB is genuinely discriminating in this dataset. Contradicting birth dates is one of the key signals that two profiles are different people even when everything else looks similar.
And config 3?
Vertex AI embeddings. Instead of pure string similarity on the address field, we embedded address strings and compared in semantic space. That handles cases like 100th Street versus 100th Street, lexically very different, semantically identical. With DOB parsing and Vertex AI embeddings, we hit 0.750 F1.
Which matches ditto.
Which matches ditto. Zero training data, no fine-tuning. Just string similarity primitives, date parsing, and embeddings. We didn't beat pseudo-wudo, 0.788 is still ahead of us, but pseudo-wudo is a pre-trained language model fine-tuned on labeled pairs. We're using zero labeled training data.
That feels like a significant result.
I think it's meaningful. The BPID paper was benchmarking whether your system cannot match records that look similar but aren't. That's a harder problem than most ER benchmarks. And the DOB parsing turned out to be more important than the embeddings, which surprised me.
Why surprising?
Because embeddings are the sexy answer right now. Everyone wants to solve data problems with vectors. But the actual improvement in BPID came from correctly parsing dates. Boring, deterministic date parsing. That's the lesson. Understand your discriminating signals before you reach for embeddings.
Let's talk about the Splink comparison on DBLP-ACM specifically. Because you said DBLP-ACM is harder than Febrl. What happens?
DBLP-ACM is 4,910 bibliographic records, academic papers. The challenge is that paper titles require semantic understanding. Author lists vary in format. Venue names are inconsistent. SIGMOD versus Proceedings of the ACM SIGMOD International Conference. Splink genuinely shines here because the Febrl-Sunter model with expectation maximization handles the probabilistic uncertainty better than a fixed-weighted config.
So Splink wins on that dataset.
Splink wins on precision on DBLP-ACM. The trade-off is setup complexity. You're writing comparison levels in the Splink DSL, you're tuning the EM convergence, you're choosing your SQL backend. If you have a statistician on your team who understands the model, that investment pays off. If you don't, it's a steep ramp.
And on Febrl?
Febrl is the easy case. Synthetic PII with controlled noise. Every library does reasonably well. The difference is narrow. It's DBLP-ACM and the real-world data where you see the gaps.
I want to spend some time on the real data wins that you don't see in library comparison posts. The blockchain work and the sanctions work feel different from the typical ER problem.
They're structurally different. In the blockchain case, I pulled 10 public blockchain attribution datasets. OFAC publishes about 800 sanctioned crypto wallets. Etherscan crowdsources about 50,000 tags across 7 EVM chains. Sourcify holds around 14 million verified contract deployments. Forta tracks known malicious contracts. DeFiLlama catalogs protocol addresses. None of them agree, none are complete, and almost none talk to each other.
And the total input size?
13,147,920 rows. Sourcify alone is 13 million of that. It dominates by 2 orders of magnitude. Everything else is a long tail of curated, high-signal labels.
How do you do entity resolution when the primary key is a blockchain address?
That's the interesting part. No fuzzy matching on names. Names disagree too often to be a primary signal. The only reliable join is the normalized wallet address, lowercase, 0x prefix stripped. The schema was 5 columns, normalized address as the joining key, raw address for display, entity name, label, and source.
And what did the reconciliation surface?
30,958 multi-source clusters. 3 findings I couldn't have produced at smaller scale. The clearest one, an address that Etherscan tagged as an exchange deposit address, that Forta had flagged as malicious, and that appeared in the OFAC SDN list but under a different entity name in each source. The only way to find that cluster is to join on the address across all 3 sources simultaneously.
And the sanctions historical analysis, the Wagner finding, that comes from a different pipeline.
Related but different. I pulled 38 usable distinct digest captures of the OFAC SDN XML file from the Wayback Machine, snapshots from 2014 to 2023. That's a decade of OFAC history as structured data. And you can compute a first listing date for every sanctioned entity.
And Wagner shows up in 2018.
April 5, 2018. Private military company Wagner. under 3 separate authorities: the CAR program, which is Central African Republic TCO, Transnational Criminal Organizations, and Ukraine EO 13660, a 2014-era authority that predates the 2022 invasion by nearly 8 years. The dominant public narrative about Russia's sanctions completely skips this. If you read press releases, you'd think Wagner was first sanctioned in 2022 or 2023.
But the XML doesn't lie.
The XML doesn't read press releases. The pipeline found it in about 3 seconds because I was querying dated snapshots, not reading narrative summaries.
What else came out of that sanctions dataset? You mentioned 18% of designations get reversed.
That's the one that surprised me most. About 18% of OFAC designations that appear in a given snapshot are gone within 2 years, removed, not just expired. That has real implications for compliance screening. If your screening database is a point-in-time snapshot and you don't track removals, you're potentially screening against people who are no longer sanctioned.
The full dataset is 85 sanctions lists, 72,000 canonical sanctioned entities after filtering.
Right. Open Sanctions has already resolved cross-list duplicates, so their canonical ID is ground truth there. My contribution was the temporal analysis from the Wayback Snapshots and the join to the blockchain attribution graph. 278,600 canonical vulnerabilities, and the joining key is completely different from the blockchain case. You're joining on vulnerability IDs like CVE, GHSA, PySec, RustSec, Go.
But OSV already has an aliases field.
That's the clever part. OSV's aliases field is a partial ground truth for the reconciliation. An OSV entry for a GHSA ID might say aliases include a CVE and a PySec. A separate PyPA entry for that PySec might say its aliases include the GHSA and CVE. The alias graph is mostly pre-computed. The ER pipeline's job is to walk it transitively and catch the cases where it isn't, where the alias graph has gaps.
What do you find when you collapse those 870,000 records to 608,000 canonical vulns?
3 findings. The one that changed how I think about dependency scanning is this. The GHSA splits into reviewed and unreviewed. Reviewed GHSA, the 28,000 entries GitHub security team actually touches, has very high overlap with PyPA and RustSec. The unreviewed 297,000 is a pass-through mirror of NVD filtered to packages GitHub tracks. When you reconcile across sources, the unreviewed portion has substantially lower corroboration from the curated ecosystem databases.
So if you're running pip audit or cargo audit and they're querying only their own database,
you might be missing vulns that appear in OSV but not in the ecosystem-specific database or vice versa. The coverage gaps are real and they're measurable from the reconciliation output.
Let's move to the e-commerce work, because that's where you got the honest number F1 of 0.05 and then showed how you got to 0.36.
Yeah, I want to be clear, 0.36 is not a good score. But 0.05 to 0.36 is a 7x improvement, and the path from one to the other is the actual lesson.
The dataset is the UCI Online Retail TOT dataset.
1,60371 transactions from a UK-based online wholesaler between 2009 and 2011. But for product dedupe, you don't care about the transaction rows. You extract unique stock code description combinations, 5,630 of them. 4,917 unique stock codes, 5,399 unique descriptions. 87% of SKUs have exactly one description, they're clean. 648 SKUs have multiple descriptions. That 648 is your test set.
No injection, no synthesis.
No injection, no synthesis. The dataset comes pre-broken. 5 distinct phenomena in the dirty SKUs. Pure typos, doily versus doily, missing E punctuation drift. Font 7 versus Font 7 word reordering, dog bowl bull vintage cream versus NL. Dog ball cream pattern renames with price changes, polka dot versus retrospot versus white spot, and trailing white space everywhere.
What was the first config?
Lexical matching only. Jarrow Winkler on the description string. F1 of 0. Femission o.re rthang.
Precision was actually okay when it matched. It was usually right. But recall was terrible. It was missing almost everything.
Step 1 to fix it. Fix the eval. I was computing F1 at the pair level, but my ground truth was at the cluster level. Pair level F1 on a cluster of 3 records undercounts by a factor of 3. Once I fix the metric, the same system looks better just from measuring correctly.
That's embarrassing.
It is embarrassing. But it happens all the time. Evaluation bugs are invisible until you question them. That's why I published the honest path, because the lesson is to question your metric before you question your model.
Step 2.
Switch from lexical to semantic matching. Vertex AI embeddings on the description field, word reordering and synonym variation, vintage versus NL, those don't score well on Jara Winkler. They score fine in embedding space. That lifted recall substantially.
Step 3.
Threshold tuning. The default threshold was too conservative for short product descriptions. Lower the threshold slightly, you recover more true matches. But you're trading precision for recall, and you need to do that intentionally, not by accident.
Final number is 0.36 F1.
0.36. And I want to be honest about what that means. It's a real improvement, it's not a solved problem. The philosophical hard case is pattern renames. Party pizza dish blue polka dot and party pizza dish blue retrospot. Same stock code, different name, different price. Is that a duplicate? Depends entirely on what you're using the dedupe data for. The algorithm can't answer that for you.
Let's talk about the hospital records walkthrough, because you did 3 approaches there: zero config, explicit tuning, LLM assisted, and they produce meaningfully different results.
5,426 CMS hospital records. The CMS Hospital General Information File, every Medicare certified hospital in the US. The problem is that Memorial Hospital appears 12 times across 6 states. Drop duplicates on all columns finds 0 exact duplicates. Drop duplicates on facility name alone flags 131 rows, but 87 of those are genuinely different hospitals. You've overmerged.
So single column dedupe is wrong in both directions.
Both directions, yes. Too strict and you miss real duplicates. Too loose and you merge hospitals that should stay separate. The hospital in Decatur, Illinois is not the same as the hospital in Jasper, Indiana.
Zero config first.
Zero config picks up obvious cases, same name, same phone, same address. It's fast and it's safe. But it misses the cases where 2 rows represent the same facility with slightly different unit designations or slightly different address abbreviations.
Explicit tuning?
You add blocking on state and zip code, so you're only comparing hospitals within the same geographic area. You add fuzzy matching on facility name with a tuned threshold. You add exact matching on phone because 2 hospitals with the same phone number are almost certainly the same facility or at least worth investigating.
LLM assisted?
LLM assisted resolves the borderline cases. Florida State Hospital Unit 14 Psych and Florida State Hospital Unit 31 Med, same PO box, same phone number. Are those the same hospital or different facilities? A string matcher sees high similarity. An LLM that understands what unit designations mean in a hospital context can make a better call.
How do phone numbers factor in?
Phone numbers in that dataset are in the format XXXXX throughout. But if you're comparing across sources, you need to normalize first. GoldenFlow normalizes to digits, then exact match on digits, same 10-digit number is very strong evidence, much stronger than fuzzy name match alone.
Let's talk about the Turkish retail dataset, because that one has some interesting data quality findings before you even get to deduplication.
The 3A Superstore dataset from Kaggle, a Turkish retail CRM. 99,998 customers, 10.2 million orders, 51 million line items. 3 things jump out before you start the pipeline. First, the reference tables use semicolons as delimiters, the transactional tables use commas. Second, money columns use European decimal format, 2031 rows, but 87 of those are genuinely different hospitals, you've overmerged.
So single column dedupe is wrong in both directions.
Both directions, yes. Too strict and you miss real duplicates. Too loose and you merge hospitals that should stay separate. The hospital in Decatur, Illinois is not the same as the hospital in Jasper, Indiana.
Zero config first.
Zero config picks up obvious cases, same name, same phone, same address. It's fast and it's safe, but it misses the cases where 2 rows represent the same facility with slightly different unit designations or slightly different address abbreviations.
Explicit tuning?
You add blocking on state and zip code, so you're only comparing hospitals within the same geographic area. You add fuzzy matching on facility name with a tuned threshold. You add exact matching on phone because 2 hospitals with the same phone number are almost certainly the same facility or at least worth investigating.
LLM assisted?
LLM assisted resolves the borderline cases. Florida State Hospital Unit 14 Psych and Florida State Hospital Unit 31 Med, same PO box, same phone number. Are those the same hospital or different facilities? A string matcher sees high similarity. An LLM that understands what unit designations mean in a hospital context can make a better call.
How do phone numbers factor in?
Phone numbers in that dataset are in the format XXXXO throughout. But if you're comparing across sources, you need to normalize first. GoldenFlow normalizes to digits, then exact match on digits. Same 10-digit number is very strong evidence, much stronger than fuzzy name match alone.
Let's talk about the Turkish retail dataset, because that one has some interesting data quality findings before you even get to deduplication.
The 3A Superstore dataset from Kaggle, a Turkish retail CRM. 99,998 customers, 10.2 million orders, 51 million line items. 3 things jump out before you start the pipeline. First, the reference tables use semicolons as delimiters, the transactional tables use commas. Second, money columns use European decimal format 200, 600, 7,001. Do it once at the source.
What else?
Moji Bake. Someone exports from Excel on a Windows machine, someone opens it on a Mac, and now your text shows cafe instead of cafe. That's UTF-8 bytes decoded as Latin 1. You fix it with a Latin 1 to UTF-8 round trip. If the text wasn't garbled, it returns unchanged. The tricky part is detecting it. You're looking for byte sequences that are valid Latin 1 but produce nonsense words.
European versus US decimal formats.
The German office writes 1.234,056 for 1,234.56. The US office writes 1.234.56. Same number, completely incompatible when you try to parse them together. The fix has to be smart. If there's no comma in the value, parse it as is. Only apply European conversion when a comma is actually present.
The Gmail dot problem is a subtle one.
Gmail ignores dots in the local part and everything after a plus sign. And John do plus spam.duo. Comma as phase is learning en. And you found 67 quality findings in under 2 threshold. You add exact matching on phone because 2 hospitals with the same phone number are almost certainly the same facility or at least worth investigating.
LLM calibration workflow seems like it wants to be more interactive too.
Yes. Right now, LLM calibration is a batch step. You run 200 pairs, get a threshold, apply it. What I'd like is a feedback loop. The agent identifies low confidence clusters, surfaces them in context, you approve or reject a few. And the threshold updates active learning driven by the agent conversation rather than a separate labeling UI. What would you explicitly not use these tools for? What are the limits? A few things. Don't use GoldenMatch for real-time deduplication at millisecond latency. It's a batch engine. If you need sub 100 ms dedupe on every API call, you need a different architecture.
Probably infiguring, probably S.
Probably an legend.
Let's talk about the hospital records walkthrough, because you did 3 approaches there: zero config, explicit tuning, LLM assisted, and they produce meaningfully different results.
Yes. 5,426 CMS hospital records, the CMS Hospital General Information File, every Medicare certified hospital in the US. The problem is that Memorial Hospital appears 12 times across 6 states. Drop duplicates on all columns finds 0 exact duplicates. Drop duplicates on facility name alone flags 131 rows, but 87 of those are genuinely different hospitals. You've overmerged.
So single column dedupe is wrong in both directions.
Both directions, yes. Too strict and you miss real duplicates. Too loose and you merge hospitals that should stay separate. The hospital in Decatur, Illinois is not the same as the hospital in Jasper, Indiana.
Zero config first.
Zero config picks up obvious cases, same name, same phone, same address. It's fast and it's safe, but it misses the cases where 2 rows represent the same facility with slightly different unit designations or slightly different address abbreviations.
Explicit tuning?
You add blocking on state and zip code, so you're only comparing hospitals within the same geographic area. You add fuzzy matching on facility name with a tuned threshold. You add exact matching on phone because 2 hospitals with the same phone number are almost certainly the same facility or at least worth investigating.
LLM assisted.
LLM assisted resolves the borderline cases. Florida State Hospital Unit 14 Psych and Florida State Hospital Unit 31 Med, same PO box, same phone number. Are those the same hospital or different facilities? A string matcher sees high similarity. An LLM that understands what unit designations mean in a hospital context can make a better call.
How do phone numbers factor in?
Phone numbers in that dataset are in the format XXXXXX throughout. But if you're comparing across sources, you need to normalize first. GoldenFlow normalizes to digits, then exact match on digits. Same 10-digit number is very strong evidence, much stronger than fuzzy name match alone.
Let's talk about the Turkish retail dataset, because that one has some interesting data quality findings before you even get to deduplication.
The 3A Superstore dataset from Kaggle, a Turkish retail CRM. 99,998 customers, 10.2 million orders, 51 million line items. 3 things jump out before you start the pipeline. First, the reference tables use semicolons as delimiters. The transactional tables use commas. Second, money columns use European decimal format, 267 EVA.
Tükenebilen. Whereas Akenebilen's dedupe. And do you have an example of where the combination matters?
A column named call7 won't match on name at all. But if every value is an email address, the pattern type scorer catches it and maps it to your email field. A column named patient identifier won't fuzzy match MRN, those strings are very different. But the alias scorer with a healthcare domain dictionary knows that patient identifier is a synonym for medical record number.
That's the domain dictionary concept.
You can extend the alias scorer with domain-specific dictionaries. Healthcare has its own vocabulary. Finance has its own vocabulary. The base dictionary covers common cases, fenvim to first name, tel to phone, and you bolt on domain packs for specialized schemas.
Let's talk about MCP. The Model Context Protocol post is the most forward-looking thing you've written. What's the actual problem it's solving?
An AI agent can write SQL, draft an email, refactor a repo. Ask it to deduplicate a 50,000-row customer file, and it will hand you a pandas.duplicates one-liner that finds 0 matches. The model knows the concept of deduplication. It does not know your data, and it has no tool that actually solves entity resolution.
MCP is the wire.
MCP is a thin JSON RPC protocol. It standardizes 3 things between an AI host, that's Claude, Cursor, whatever agent runtime, and an external server tools, which are typed functions the model can call, resources, which are readable artifacts the model can pull into context, and prompts, which are pre-baked instruction templates. The host handles the LLM. The server handles the work.
And you're exposing the Golden Suite tools over MCP.
Each package maps naturally. InferMap becomes map schema, takes source and target schemas. GoldenCheck becomes profile and quality report. GoldenFlow becomes clean, GoldenMatch becomes dedupe. GoldenPipe orchestrates the full pipeline. The underlying functions already accept file paths, return structured results, and stream progress. Wrapping them as MCP tools is mostly metadata.
What does this actually unlock in practice?
The interesting case is conversational data cleaning. A user drags a CSV into Claude and says, "Make this usable." The agent calls the profile tool, sees 18% missing zip codes and 3 different date formats, calls clean, then dedupe, and reports back 5,426 rows in, 4,891 golden records out, 535 fuzzy duplicates merged. Here are 12 clusters that look low confidence, want to review them. No code written, no docs read.
The agent is doing the data engineering.
The agent is doing the data engineering. And critically, it's using real tools that produce real results, not generating code that might work and might not hallucinating column names, not pretending that drop duplicates solves the problem.
Schema mapping inside an ETL agent.
Today, mapping a vendor's column names to your internal schema is a human-in-the-loop chore. With InferMap as an MCP tool, the agent can call map schema, get confidence scores and per-scorer reasoning for each mapping, and either apply the high-confidence ones automatically or surface the low-confidence ones for review. Same contract regardless of whether the host is Claude Desktop or Cursor or a custom agent.
What's on the roadmap from here? Where is this going?
A few directions. GoldenMatch TypeScript is the obvious next port. If you can run GoldenCheck and InferMap in a worker, you want deduplication there too. That's harder because ANN blocking is compute intensive, but the small dataset case is very tractable in the browser.
What's the small dataset use case in a browser?
Real-time dedupe on form input. You're in a CRM and you start entering a new contact. The browser-side dedupe runs against the local cache and says, "This looks like John Smith from Raleigh, is this the same person?" Before the record ever hits your database. That's a qualitatively different user experience than batch dedupe after the fact.
What else?
The MCP integration needs more tool surface. Right now it's the core operations. What I want to add is streaming progress for a 400K record run. You want the agent to see incremental output, not wait 40 seconds for a result. And richer resource exposure, not just the final output, but the intermediate blocking stats, the confidence distribution, the low confidence clusters that need review.
The LLM calibration workflow seems like it wants to be more interactive too.
Yes. Right now, LLM calibration is a batch step. You run 200 pairs, get a threshold, apply it. What I'd like is a feedback loop. The agent identifies low confidence clusters, surfaces them in context, you approve or reject a few, and the threshold updates. Active learning, but driven by the agent conversation rather than a separate labeling UI.
What would you explicitly not use these tools for? What are the limits?
A few things. Don't use GoldenMatch for real-time deduplication at millisecond latency. It's a batch engine. If you need sub 100 ms dedupe on every API call, you need a different architecture, probably an embedding lookup against a vector index, not a full match pipeline.
What else?
Don't use the zero config mode on unfamiliar structured data and trust it blindly. We just showed that on the Bulldozer dataset, zero config produced zero matches. The auto classifier has real failure modes. Short integers look like phone numbers, round 5-digit numbers look like zip codes. Profile first, understand what the auto config decided, then either accept it or override it.
And the LLM features?
The LLM scorer is for borderline pairs. If 90% of your pairs are clearly matches or clearly non-matches, LLM scoring those is a waste of API budget. The LLM earns its cost on the ambiguous 10%, calibrate that before you enable it on a large dataset.
One thing I notice across all your posts is that you publish honest failure numbers. The 0.05 F1 on the retail catalog. The 0 matches on the Bulldozer first run. The footgun in dedupe that crashed mid-partition. Why?
Because the failure modes are the most useful information. Everyone publishes the tuned result. Nobody publishes the first run that produced 0 matches. But the first run that produced 0 matches, that story tells you more about the column classification problem than the final tuned result does. And the evaluation bug on the retail catalog, that teaches you to check your metric before you blame your model.
The NPPES post explicitly says faking the test data to prove a point is cheating.
Because it is. If I inject synthetic duplicates into NPPES to benchmark against, I've chosen my own ground truth. I'm testing whether my system can find what I put in. That's not interesting. What's interesting is running it on data you didn't design and seeing what it finds. Sometimes it finds 10,718 clusters in 34 seconds. Sometimes it finds 0 because you misclassified your columns. And sometimes it finds that Wagner was on OFAC 4 years earlier than the public narrative says. Yeah, that one actually surprised me. I went in looking for cross-jurisdictional sanction alignment, whether the US and EU and UK lists agreed on the same entities. I wasn't looking for a timeline correction. The pipeline surfaced it because it was querying structured XML snapshots, not searching for a particular answer.
That's a pretty good advertisement for letting the data speak.
That's the whole project. The pipeline should tell you what's in the data. You shouldn't have to tell the pipeline what to find.
Last question. If someone is listening to this and they have a messy 200,000 row dataset sitting on their laptop right now, what do they do first?
Profile it. Don't write cleaning code, don't write matching rules, don't reach for drop duplicates. Profile it first. What are the column types? Are phone numbers stored as integers? Are there dates in 3 different formats? Where are the nulls? What's the cardinality of each column? That takes under 2 seconds on 200,000 rows. Everything you do after that, the cleaning config, the blocking rules, the match threshold, should be informed by what the profiler found.
And if the profiler finds something surprising?
It will. It always does. And that's actually good news. It means the profiler caught something that would have broken your pipeline downstream. A zip code column stored as integers is going to silently strip the leading zeros on every Connecticut zip code. A date column with mixed formats is going to cause parse errors at 3 a.m. Finding it in stage 1 in 1.1 seconds is infinitely better than finding it in production.
On that note, profile first. Trust the data. Thanks for being here.
Thanks for having me. This was fun.
That's the show. The Wake County voter file, the Bulldozer auction data, the blockchain attribution graph, the 10 years of OFAC history, all of it is public data. Download it, run it, see what you find. If the pipeline finds 0 matches, that's probably a column classification problem. Check the config before you blame the algorithm. That's all for this episode of Dose of Data. Thanks for listening.
If you want the code, the blog posts, or the datasets we walked through, everything is open at bensford.dev. See you next time.